All right, if everybody can settle in, we'll get our session started. I'd like to start right on time if we can. All right, thanks for coming to the session. We've thought this would be an interesting kind of alternative style of an AGU session to have. Directing a session on innovations and future thinking in the space physics and aeronomy area is pretty is timely in our area for at least three reasons. And one of them is that we have a real call to arms, and it actually comes from several places, several strategic planning documents, including the Space Weather Action Plan, which really gives us solid metrics that we should be going after in terms of what society needs from our community. And in addition to that, there's always the discovery element of what we do. As we explore things like exoplanets and so forth, we suddenly have a real relevance to understanding the details of how our stellar planetary system works. Second reason for the session is, I would say, is technological, in that there is a lot of technology that can be leveraged, and we're going to hear about some of that today, including cloud-based infrastructures and opportunistic measurements from things like Ampere. These are things that benefit specifically our community. And the third thing, which I think we'll hear about in at least one talk, is kind of social. I mean, there's a various, for better or worse, topics that are really at the fore right now in terms of how we interact with one another as a society, and I actually believe these play into things we want to do when we start looking at distributed measurements and how to aggregate all of that together. So I'm going to leave it at that and introduce our first speaker, and that'll be Larry Paxton.
Thank you, Josh. So I think we live in a fundamentally different age now than we have in any time in the past. And part of it is coming to the realization, as Josh said, of what that empowers in all of us. And so the title of the talk, Now Age, New Space and Transforming the Exploration of Geosciences, is one of the ways of looking at that. Now, what we really are trying to do, as many of you heard me talk about before, is the S-curve that we're on. And what we want to do is figure out how we transform ourselves from one S-curve to another to increase our happiness. So the Now Age, this is a term I've coined in a couple of papers I've written on innovation and social organization. What it is really we exist in a fundamentally different time. As Josh said, we are connected in a way that we've never been connected before. In science, though, we typically don't take advantage of that very much. And this is a way to both inculcate in our audience an appreciation for what we do, but also to push the boundaries of how we do it. And so that now age means that in our society, people expect to have information now. And what we need to be able to do as a scientific community is be able to see that data, interact with it, and produce results now. So there is ubiquitous connectivity that we can take advantage of. We have low-cost data storage. We have, of course, memory. We have CPUs, GPUs that we're able to take advantage of in order to produce results. But part of that is a culture that enables us to share those results. And I don't think we've really done much with that. And I'll try to illuminate what I mean by that in just a second. So with that, we now have the ability to do many things we've never had before, which is we have ubiquitous, cheap access to space. So now, here's some physical realities. We're competing with for resources with many people. And so in our little cloud-like community that we sit upon, we are interacting with, we have discovery, innovation, and opportunity that interacts with the available funding. Now, the problem with that is that talent will be attracted to areas where there's more money. Unfortunately, we're in a situation where either the money is decreasing, which leads to an exodus of talent, or even remaining the same, in which we compete less effectively for talent when there are pools of money, like say in computer science, artificial intelligence, robotic cars, all of that are attracting talent that we may be able to use. When I was a kid, space was an aspirational goal. We talked about the space age. That was what people were a part of. We fundamentally envisioned a future that was different from what we did every day. But now people think really in terms of a future that's just more of the same, more information, more stuff. So how do we inspire that generation? Well, our challenge is really, I think, to turn heliophysics into a discovery mode science. Now, I'm going to repeat this theme many times, and I'd be glad to talk about it in great length, but I will not, is that we have opportunities within our reach. And some of those is recognition of the current way we do science. We need to create an inclusive culture that gets different perspectives. We need to be able to address this phenomena called learned helplessness. And I'd be glad to talk about that at length later on. We need to accept that science is not valued by many of the people that fund us. And we need to inculcate in our public, in the people that pay the bills, a sense of wonder about what we in heliophysics do in particular. So one of the topics I'm only going to touch on is that when we think about what we do, what we know, we have to realize, we have to be able to convey, honestly, there are things that we do not know in order to empower this vision of us as a discovery machine. And one of the things that is a problem is that we have not yet really fully embraced the limitations of our ability to model the phenomena. And by embrace it, in a tight money situation, it's often difficult to admit your model isn't perfect because that would expose you to the other competitors who say their models are perfect. But it's only in those gaps of knowledge and ability to predict and understand that we have opportunity. And so there are things like exploring the limits of predictability and developing new techniques like assimilative techniques that help us understand the phenomena better. A key idea is enabling innovation. And so there are flight opportunities, data capture, instruments, and visualization. I'm just going to talk about that. But the key idea with all of this is the unenlightened that we deal with all the time know the cost of everything and the value of nothing. And our challenge is to create messages that connect with people. So one of the messages I think about we can craft is when we talk about heliophysics, we can frame a set of questions that are I wonder. And I'm going to just go through these quickly. I wonder, how unique is the Earth? How does solar variability and the connection affect the evolution of a planet? What are the factors that define whether you can live there or not? How do we predict this complex coupled system? What does it tell us about other star systems? How do we enable cost-effective solutions? How do we create a new society? That's really what our goal is to create a new society as part of this new now age. And what do we need to know in order to be able to execute that? The big idea of all of this is that heliophysics uses a natural laboratory that is our Earth connected to our sun to help us explore both the solar system and help us understand our context, but also what happens in other worlds. Now, there's another set of people that want to know about heliophysics, and they're the ones who say, I need to know. Not I want to know, but I need to know. I need to know how to operate with assurance in a space environment. I need to know what happens if there are human-caused events in space that affect my operations. I want to be able to separate natural from man-made occurrences. I want to be able to tell what's happening to the upper atmosphere and the ionosphere. I want to be able to predict collisions. I want to be able to decide where RF waves are going to be propagating. I want to understand and I want to know how to predict these things. I want to fundamentally improve my bottom line by understanding the space environment. So the big idea there is we are at the limits of our engineering solutions. And what we need to be able to do is take our community's understanding of the science and convert that into the I need to know answers. So we have this complex system. This is one of my favorite pictures. Many people say that it shouldn't be, but it is. And what it tells us is something fundamental. It isn't that it's so complex. See, some of the scientists marvel at it because it's so cool. There's so many things going on. But it's what's really the fundamental thing we don't know about it. We cataloged all these individual phenomena, but what we don't know is how do they work together? It's all of the coupling that's the fundamental frontier for us. And what we need to do to understand that coupling, because there's so many free parameters, if we don't get the coupling right, we can't really test our understanding. We can't really predict the future state of the system without constantly tweaking it. So, what are the key enablers that are within our grasp? We start off by asking, we ask questions and we have answers and we compare the two. Sometimes it's been done by analytic processes, but one of the things is we often assert with religious fervor certain measurements must be made. The problem with that is when we look at a system that's as complex as our own system that I just showed you that snapshot of, how do we manage the next mission, say GDC? You want to measure everything all the time, everywhere? Well, yeah, that's great, but can we afford that? So how do we figure out what we really need to do? Well, one of the things we can do is we can start to ask a set of questions. We can posit an investigation. We can run it through models and see what would you be able to measure. Then you compare that, where you visualize it, you apply analytics, and you get answers. Now, obviously, there's something wrong with this picture. We do this by a technique called observing system simulation experiments. And assimilative models are ones where you take data in and you sort of fill in the gaps. But you can see the biggest gap in this picture is we haven't connected the answers to the questions. Now, the assimilative models, what they are able to do, and I'm only going to touch on this for a second, is you take different sets of data, you develop a self-consistent picture based on the data of what that system represents, and you compare that so that you can understand what are the gaps in your knowledge. You understand the sensitivities of the system. And what we can do with this is we can design cost-effective missions. And one of the things I want to emphasize is we need space-based and ground-based observations working together to be able to produce this picture. It's only when we're able to produce data that can be compared to the models, and you see in this image here, I've got data with two hooks. One is where you compare it to models, and one where you assimilate it into models. And then those, you then visualize and compare, and you develop an understanding and posit answers and questions. Now, what are the techniques? In there I mentioned visualizations. Now, this visualization technique, we're still pretty much trapped in the 17th century picture of graphs. And even many of our movies that are just one graph after another are still the same thing. So this is one of the things we can do is GPUs, graphical processing units, produce enormous amounts of computational power, and they can produce these very detailed pictures. Who knows if any of that detail is right? But you know, you can, with a GPU, you can make plots like this. Now, if you're like me, you want to click on those buttons. You want to mess with it. You want to interact with it. But one of the cool things about a GPU is that not only can you interact with it, but you can record that interaction and share it with somebody else, so it becomes a collaborative tool, a 3D visualization. Instead of me sending out a graph and publishing it, and you just take it and make your own conclusions, I can have a curated data set, an interactive visualization. And so the code for that is pretty complicated. That's the entire code to make that picture. That's the revolution in our abilities. What we can do is that there's an entire branch of study of how you understand how to communicate this information. So what we can do is we want to communicate the excitement of our science. We want to have the ability to do crowdsourced analysis. That's something that's enabled by these techniques. Curated exploration of the data, where an expert shows you what it is in the model that you should see in this four-dimensional set of information. We don't do anything like that. And then one of the most powerful things of all that GPUs enable is interactive, in situ instantiation of the model. So if you see the run is, you think it's going to follow a particular trajectory, let's say we're looking at temperatures or densities, you can tweak the inputs in this in situ as you're going along and record how you do that, and explore the gaps between what is observed and what is predicted by the model. So this is what we get, is a system like this, where the instrument's in space, and a suborbital means not only the suborbital like rockets, but the kind of suborbital they refer to in Earth science. They call anything that doesn't go into space suborbital. So that means ground-based as well. So they offer this sampling tech, and one of the things we need to realize in all of this is that each platform offers both limitations and potentials in terms of the spatial and temporal variability that they're sensitive to. And so some of the things that we haven't explored in our community are stratospheric balloons to loft payloads above the atmosphere that causes, that blocks the radiation that we would like to observe. In the UV, for example, and also things like sailbots. And these are commercially done things right now that we could take advantage of. Autonomous vehicles that can patrol the oceans and take data. One of the other things that, just as a frontier thing that I think we can take advantage of as well is additive manufacturing, and instrument designs can take advantage of what's available as commercial off the shelf. Now you say, am I going to build this thing and fly it? Well, no, the thing that you do is it's useful for prototyping designs, because one of the problems if you've ever built an instrument is the first thing is you come up with a design, and then all the engineers put their designs together, and then it doesn't fit. The other thing is, well, it may fit, but nobody can reach their fingers in to actually assemble it and make the connections. And these are the kind of things that are very difficult to accommodate in a cost-constrained environment. And so one of the things, too, is you want to look at things like, are the instruments going to work? Now, there are new platforms, and we may hear some interesting things later on about what's going to happen with potential lunar exploration. There's a deep space gateway, an assist lunar observatory, that would give us access to images like this one from Apollo 16 of the Earth, which tells you basically most of the phenomena that you ever want to observe. Now, there's other platforms like OneWeb. OneWeb is a global internet access. You may say, well, that sounds crazy. Who's going to pay for that? Well, they've already raised $1.5 billion. They're going to revamp the manufacturing of a spacecraft. Why is that important? Well, first, they're going to build 15 satellites per week. One of the problems we have with NASA right now is the costing of constellations. There are no good cost models for reducing the cost when you make more than one copy of an instrument or a bus. That's our frontier. They're going to build 900 satellites, and they're going to cost less than $500K and provide global internet access. Well, that's cool, but it's low-cost internet access from anywhere. That means our remote instruments that we can't service and command now, we could do that. We could even potentially communicate in space. Big companies like Blue Origin and Aeronomy have decided, they've locked into this, this is going to happen. So what we want to do, there's autonomously operating stations that we can use, the ability to move data from the user, this last mile problem, the ability to control it remotely. The sailbots I mentioned is just one of those ideas, unmanned aerial systems that are able to linger at stratospheric altitudes above the radiation cutoff at 308 nanometers for weeks at a time. And reconfigurable observatory for looking at phenomena in the atmosphere, high altitude balloons, CubeSats, affordable propulsion, and so on. So basically, I think the future, is out there, and that's what I wanted to leave you with a message. We can talk about this much longer. I only have a few minutes, and look, the light's blinking. So
you're done.
I'm done. Okay, so that's it. That's all I was going to say. We're all done, and thank you very much. I appreciate the opportunity.
Thank you, Larry.
Thanks, Larry.
Thank you very much.
All right. Yeah, we're going to actually move right along. That's one sure way to not raise any controversy is to use all your time. Let's see if I can figure this out. All right, so there's that.
Okay, so set your timer for 13 minutes. So it'll be Oh.
Really? I have no idea how to operate this screen. It's not this one, I guess. Is there a mouse somewhere? We need a mouse. It's not this one. It's supposed to be this one.
Is the mouse turned on? Now it's on.
Yeah, do we have our technical support person handy?
I don't know.
Oh, it's
There we
working
go.
again.
All right.
All right.
Wait.
Now this mouse just dropped out on us for a couple minutes.
It's probably low on batteries.
Think. Yeah, we can't move on right now. We don't have any mouse control over the screen.
It keeps dying on us. Okay, hang on.
I'll be right back with the physical.
Yeah, can you get to my, oh,
You're on, I think you're right here. Yeah, you're here, right? No, I didn't. Can we get to that?
That's me, sorry.
Oh, can you get to it from there?
Nope.
Connection.
I got it moved. Where is she?
Jaynes right here.
You have to click it, double click it.
I know, really. I tried.
No.
Yes.
All right, I think we're there, right? All right. Oh, no. All right, how do you, what's the keyboard command? F5.
Yes.
Yes.
All right.
Okay. You ready?
Yeah, Allison Jaynes, taking risks for the future of space weather forecasting.
Okay, thank you. All right. So when I was invited to give this talk, the conveners asked it to be more of a TED Talk-like presentation. So I did go through and do some research on how to give a TED Talk. And it turns out that for the most part, they seem to be a somewhat random collection of ideas that build up to a somewhat tenuous conclusion. So that's what I have for you today. So I started off with the question that I wanted to ask, which was how can we all take more risks and embrace uncertainty as opportunity? And I have some more specific ideas about that. So the first thing that we all know we need to do is support new technology, right? We need to have those pathways in place. And so lines such as the existing H-Tides ITD are extremely helpful. And the question I'm asking here is, should they be more guided, in fact, so that we are lining up new technology with an eye towards what's coming down the pipe for the decadal survey missions? Should we be thinking about funding things or asking to fund things that are within a certain mission scope so that we're looking towards that decadal survey? Also, competition, we all know, is very healthy, makes for arguably better proposals. But I'd really like to ask the agencies to be clear in their funding aspirations. So when they say we want to fund brand new technology that's never been seen before, well, then that's what I'd like to see them fund. On the other hand, if they're asking for something that's been done before and we're going to get a big science return because it's proven, then that's what they should ask for. But just to be clear so that we all know what we're proposing towards when we put in these proposals. And then the stumbling block I see is how to get these off the ground, but I'll talk about that in a couple of slides. Small sats, they can really deliver these days. We know that. The shining example, I think, is CSSWE, or the Colorado Student Space Weather Experiment. This was an NSF-funded, under $1 million Cubesat, which has been wildly successful. They've had 20 peer-reviewed engineering and scientific papers, including 2 in Nature, one that's coming out, I think, this week or next week, in which the results are based solely on CSSWE data. So like the first Nature Cubesat paper entirely, and not just supporting data, which is quite amazing. The risks that were taken here were many. As you have already seen, if you've seen Shinlin or Lauren's or Quinton's talk on CSSWE, that antenna there that you'll notice sticking out from the Cubesat, upon closer inspection is actually just a tape measure that you can buy at a hardware store. And so there were lots of these inventive components that were taken from off the shelf or from hardware stores locally that ended up being big risks, but with a big payoff in the end. This was followed by many other successes, and I think that this Cubesat and then the others that followed have really increased our enthusiasm for Cubesats as scientific platforms, and then also increased the pace of all the subsystems technologies that go along with that. So that's been really great, but I would also like to point out that I think Cubesats are precisely the platform that should be used to take these big risks. And so if you want to try and push Cubesats toward more in the Class D range, then you can do that as long as you keep these high-risk Cubesat funding lines in place so that we do have that platform to work with as well. For our access to space, we need to look towards a sharing economy, I think. We all know that multi-point measurements are the key to, you can't even really propose a mission these days unless you have multi-point measurements involved, But with more spacecraft, we need to think about how we're going to get all of these spacecraft up there. So one of the ideas that has already been utilized is this concept of a hosted payload. Gold will be one of the first NASA missions to be a hosted payload, launching in January, hopefully. And this, I think, can be replicated towards other missions in the future. But we also need to look at rideshare launches. There is a direct need right now for more pathways to ride sharing, and any of you who've been involved in this sector know that. And really that requires a coherent and forward-thinking policy from NASA. So I'd like to see something come out of NASA where everyone agrees, and that means proposal review panels are all in agreement as to what constitutes risk when you're talking about ride sharing, not just on CubeSats, but also on small sats and larger missions as well. I think that the motto around NASA should be let no ESPA port go unused, because there's a lot of ride opportunities that are out there, but we're just not being able to utilize them at the moment. And so this would also require coordination of CubeSat and smallsat launch opportunities, which I think NASA centers are uniquely placed to contribute to, but that just needs to get going. And again, there has to be a very coherent policy in place, which does not exist at the moment. So the future of space weather research and operations, as I see it, we need at least an order of magnitude more data points. This is to even get close to the kind of terrestrial weather forecasting that people say they would like space weather to be at in a few years or in 10 years. And so that order of magnitude is going to require, of course, a big leap in technology and a big leap, I think, in risk-taking as well. There needs to be this pipeline from research to operations and then back around again that moves at a quicker pace so that we're updating our forecasting models in line with when we understand things better, maybe not 5 or 10 years later, but really immediately, again, as they do with terrestrial weather right now, and we're not really at that place right now. And then I think that space weather has to have a focused system of observatories, similar to how we have when we talk about the HSO, but something that's really directly focused just for space weather if we really want to tackle this problem and solve it. And along with that, you have to define these critical data points that you want to measure. You're not going to have everybody's instrument coming on board to these small satellites in this network around Earth, right? You're going to have these 1 or 2 data points, measurements that you need, that you think you most need to get that space weather forecasting to work. We need to agree on that, and then that's what needs to be the first swarm that we send out. And we haven't defined those at all. So miniaturizing the technology, of course, goes right along with that. We have to get smaller instruments so that we can make these cube or small sats and be able to put them out into these order of magnitude more data points. There's some barriers still to research that I think we need to break down, and that can be done. So there's a program, for example, helmed by the University of Colorado called INSPIRE. It's basically an international consortium of universities and research institutions, and what they do is they work on they have their direct goal of building a small satellite and then launching it and doing it with a low cost. And this is using cost-sharing models so that NASA, for example, is not holding the entire burden of the cost of those spacecraft, but it's being shared among other countries. This is working really well so far, and I think this can be replicated at other institutions and other agencies, and should be. And along with that, but maybe slightly different vein, it should be really much easier to work internationally than it is. And this includes getting small grants to be able to, say, host your instrument on someone else's payload. Right now, that's pretty hard to do, even if you have a complete instrument, but you just want to send it off to someone else's CubeSat or someone else's sounding rocket in another country and get that to have a flight test. So that should be much easier to get through those barriers as well. So what other kinds of barriers do we maintain? It's not just this international or geographic barriers, but we also need to broaden the demographics in our field. And I hope other people in this session will bring this up as well, but I'm going to tell you my thoughts on that. So we can broaden the pool from which we draw such amazing talent if we just make the community more welcoming and more inclusive. And we have done that, and we're starting to talk about that, but that needs to go much farther. There are lots of different ways in which we can be diverse from each other. Diversity doesn't simply mean more women. Yes, it's great to have more women, but you can't just hire more women and say we're done. Okay, there's these other avenues that we need to look at to get people with different ethnicities, races, sexual orientations, gender identities, and then even socioeconomic backgrounds, which is one of the hardest ones to be inclusive towards. And I think all of us can promote inclusion. It's not just pointing at this agency or this funding pool. It can be from proposal panel groups all the way up to, or all the way down to, graduate admissions committees, where you can say things like, let's not look entirely at GRE scores, which are often directly related to someone's socioeconomic background, and how well they do on those tests has direct correlation to that. But instead, look for leadership qualities, look for creative thinking, and go from there. And that can be done at everyone's institution, even academic admissions committees. Early career opportunities is in this same category. And I'd like to point out that early career opportunities should not just be promoting someone in their early career, but also giving them the chance to have a challenge. So I actually had this written as not early career investigator program, but something else. And then last week, the announcement came out that there was, in fact, an early career investigator program in heliophysics. So yay, that box is checked off, done. But I would encourage all early career researchers to look at that text, to look at that draft, and provide feedback before that deadline to see if that aligns with what we're all thinking could be useful for early career programs. There's also the fact that we could be creating opportunities for more junior PIs or early career PIs where they have a record of being such a title, so that when they are going to propose their own missions, people on proposal panels can see that they were mentored with a more senior PI, and they've gone through this entire process before, and so maybe they'll feel a little bit better about taking a risk on that person. And then embracing interdisciplinary research is an obvious one, but we still don't do enough of it. This is teaming up outside of our field and crossing the lines of our little subdisciplines and having more of a culture of transferring knowledge rather than hoarding it into our own little sections, but sharing it and seeing what can come of those partnerships. Okay, my last thing here is that I think we need to be a little bit more visionary in heliophysics. Astrophysics and planetary both have these long-term vision plans, and they're looking 30 or 50 years out. Heliophysics, we still only have our decadal survey. So I wonder why that is, and a lot of us early career researchers have been thinking more about that. I think it would be really useful to see where we're going long-term. Even if we don't yet have the technology to support some of our ideas, we still should be having that goal. You know, talking about, for example, what does a space weather forecasting network really look like? Because I'm not even sure, and I don't know if it's been fully defined. Okay, so this is my summary. I think we should take risks. I think we should then take more risks. We need to open pathways for new technologies and mission concepts, cross field lines, bet on someone new and unknown, and definitely talk to and work with people who are not exactly like you. Thank you.
Okay.
Or no, I don't know.
Any questions?
Yeah, thank you.
Yeah, thanks.
Paul.
So that was excellent, really wonderful, covered a lot of great topics. One thing I didn't see much discussion of, which maybe my pet peeve, is model sharing. We have robust data sharing policies, but we still treat models and the support codes that build those models as proprietary intellectual property. And I think that's also holding us back.
I agree. I'm not a modeler, as you can tell. But you're right, the models need to be shared, or should be shared as well, because that is something that's holding us back. Terry.
Yeah, one more.
You mentioned trying to get more data points out there. I'd like to hear, what are your views on doing utilizing better the data that we already have? It seems like we have just decades of mission data that I believe have been underutilized. And perhaps with some clever modern machine learning techniques, we could mine that better and get it incorporated into our models better. Maybe that isn't risky enough.
No, I think you're right. I think that Jacob is going to actually talk about that point exactly. But I will point out that we have decades of 2 or 3 point observations, and we don't have decades of 100-point observations or more, which is one of the things we actually really need, which would be different than what we've done in the past. But I do agree with you, and Jacob will address that in his talk.
Okay, thanks very much.
Thank you.
Okay, next we're going to hear from Brian Anderson, who's going to talk about science innovation through industry partnership.
So speaking of 100-point measurements, Ampere stands for Active Magnetosphere and Planetary Electrodynamics Response Experiment. It's based on the Iridium constellation of 70 low Earth orbiting satellites. And I'm going to start out with some platitudes, and then we're going to do story time. So let's see, which is the next here? Oh, what do I do next? Left click? Hey, left click, okay. So I'm going to start off with the summary, just in case I don't get there. The commercial partnerships are another avenue that's out there, and we've seen one example that's coming. This is one that's been there, and it's being replaced, and it will be there into the 2030s, okay? And we already know how to use it. They can offer a huge benefit for a modest cost, but they may not offer the design flexibility and customization that we're used to with NASA missions or even with our ground-based things. You may not be able to point them where you think, or they may not have the performance that you need, and you need to be able to think, well, then what is it that I'm getting? What can I do with that? And also, there can be a huge disparity in timelines. Commercial scales timelines can be in months when you have to make a decision about you want to do something and come up with $5 million to do it. That does not work with the federal acquisition techniques and processes. So the best way to take advantage of a commercial platform is if you have a rolling or quasi-continuously available opportunity. And you'll see that play out when we get to story time. And then the other one is if you have to be honest and straight and respectful. This is the kindergarten slide, okay? So you got to be honest with yourself about the science you want to do. What's the real science that can be done? Go ahead, be critical, be self-critical. Don't be a cynic, but be critical. Don't oversell it, because if it doesn't really close, you won't win, okay? That can be applied to anything. And then you have to be honest with your prospective sponsor. It may not be their fault that they can't turn on a dime, okay? There may be very good, legitimate procedural process reasons they can't turn on a dime. So if you have a new innovative idea, get them used to it. Proposing something novel that's completely out of the blue that they weren't expecting, you might well get the response, that's not how we do things. Even though they asked for innovation and novel things, you propose one and you think you're being double turned on, but that's not the case. So understand their constraints and their larger goals and give them time to adjust. And then be honest with your partners. You have to establish a relationship that's going to weather difficult times. And that means always keeping them in the loop and being straight with them and realistic. Okay, so now it's story time. So way back when my career was starting, and yeah, that was a long time ago, this is sort of what we knew about Birkeland currents, is that things get more active, they expand in lower latitudes, and they get more intense. So with a fish analogy, this should be pretty easy to tackle. We shouldn't have a problem with that. So then I started to say, well, let's study storms, okay? So we're studying storms, and this is an example plot from UARS. And oh my gosh, there's an awful lot more than just two currents, and they change from one pass to the next. And whatever this is, it's not just pairs of currents. And it changes completely. It's too fast to follow, and basically we need a bigger boat, okay? If we're going to tackle this system, one satellite ain't going to do the trick, okay? So then that was back in 95. This is some of the stuff that was hot and cool in 95. Some of that stuff is still around. This little guy and that thing are still around. Okay, and this is the thing that I had in mind back in 95 when I saw that we needed a bigger boat. I said, aha, that's bigger. That's like 70 boats. Then maybe that can do something useful. So the genesis of the idea actually goes back to the 1995 Spring AGU meeting in Baltimore. After the meeting was over, Dave Klumpar and I were sitting out in the veranda And he was with Lockheed at the time, and they were building the Iridium Block 1 satellites. And he had contact with an engineer. He sent me that, and he confirmed that all the birds were equipped with mags. It was part of the attitude determination system. They were bounty mounted. No booms. Okay, you got to live with what you get, right? Okay. And they had no idea what the downlink plan was. Okay, we knew they were sampling them like crazy on board, but we had no idea what the downlink was. So, but still, it was 70 satellites, and the orbits looked like a great place. You know, they were near polar, the even longitude spacing, 9 minutes in-track separation. You know, this might be the boat, you know, that we need. All right, well, here's the story. So the first lesson is persistence. Don't nag, but be persistent. So I called an Iridium engineering contact. This is almost verbatim, okay? Well, he didn't work for him, so try somebody else. Okay, so I tried another guy. That actually worked. He answered for him. He still worked for him. That's pretty cool. And this is what he said. Okay, right. Okay, so that's where we were. So then he asked, and then that's what I did for the next, like 12 months, okay? And then I'd send another email, and I'd wait and so forth and be patient like that. But, you know, it's not gray, right? That's how you know I was younger then. So anyway, then, so you got to be proactive. So this is an act of daring do that went on here. I still can't believe I did this. So there's another follow-up email that I intended to submit the idea to NSF. Okay, so I'm being straight with these guys, right? Silence. So then I proposed to NSF to study how I would use the Iridium data while working to acquire some. Okay, I still hadn't seen any, and I had the guts to propose to do this? Oh my God. Well, that's what I asked for. They gave me that. And even that is pretty brave. So there was one brave, savvy program officer, and by the way, you know who you are, okay? So they actually did that. And then I sent another follow-up email to Iridium, and there's, kind of what I said. And then the phone rang, and I had to, I seatbelted myself to my chair just in time. And so it was a VP for Iridium that asked this question at one of their meetings. And I had just sent that guy an email, okay? So, sometimes you got to get lucky, and that's what happened. And that's where the persistence but not nagging, because you want them to think at least not too negatively of you when they're looking at that email, okay? That's the thing, all right? So anyway, that's not me, by the way. And so, then I get some files, okay, and I was so excited because they were enormous, okay. Unfortunately, they were ASCII files, and they had the date, the vehicle, the name of the parameter, the receive time, the sample time, the vehicle, and there was the magnetic field in Teslas, okay, to 6 places. And there were some words that came to mind that can't be said in public, okay. And so then I got in touch with them. Unfortunately, it was a database query, okay, so they could change that, but they could not make them more sampled off in more than 3 minutes. That's 15 degrees in latitude, and the system we're looking at is 5 degrees wide, okay? Ouch. So I said, can I get, like more data, like another day? I said, no, like months of it. And he said, oh, well, why don't we just send it all to you? Would that be okay? Are you sure? That'd be fine. Thanks, that's great. Okay, so this is where you got to be straight. So this is a plot I've showed before, but I got some data from the vehicles. If you line it up in latitude, oh my God, look at that. The damn thing works. How about that? Hot dog. And the first abstract I wrote said the noise level was about like this. The engineer said, no, that's the noise level. And I said, no, that's my signal, guys. And so that's really true. But I was straight with them. I said, this is great. I can maybe get some grants to work with this stuff, but I'm not going to be able to send you guys any money unless I get like 10 times more data. That's what I really need, guys. And that's where you got to be straight. You got to be straight with yourself, what you need, and with your partner. All right, but they took an interest in that, and they found a way. This is the telemetry that they were sending down. That's the magnetometer data. The magnetometer data was packed with all that stuff, okay? And they found a way using another communication protocol to design a custom packet that the spacecraft pushed to the ground. And then also, that's what they do, at least in the Block 1 satellites. So they had that figured out, okay? Well, so here's more of the sob story, right? But I'm actually not crying anymore. So the first mission of opportunity we proposed was in 1999. That was dropped because the Iridium was funded by Motorola at the time before Iridium went bankrupt. That's the next bullet. And they could not send money. If I sent them money from NASA, they could not take it because they were a private company. They could not abide by the FAR. So that was the end of that proposal. And then things, kind of went very scary in 2000, and a new company was formed that employed exactly the same technical people. They just shed the debt because what happened is your cell phone systems took off and that took away their market right from under them. Anyway, so then a second mission of opportunity was in process in 2001. That was canceled when the exploration initiative was announced, and so that was dead. I remember the phone call from Haya telling me about that, and he said, "Is that a problem?" And I said, "Do you think?" And so anyway, then mission of opportunity, we tried to apply to this. This is an example where you got to be honest with yourself. And the fact is, I just couldn't make Birkeland currents close enough to RBSP science. And I mean, it wasn't the fault of the review panel, the science just didn't really fit. So then I was briefing Iridium and Boeing the whole time, and I briefed NSF. They asked for a proposal in 2007. So you got to be persistent. Look at the time span, okay? My first proposal was in 1995. And I finally got a proposal in 2007, okay? Oh, well, and that's not the end of the interesting stories. We were selected for funding. That is awesome. And I tell you, this is absolutely how it happened. On the 14th of January, 2008, I happened to be the magnetometer scientist for Messenger, and that was the date of the first flyby, our first encounter with Mercury since 1975. And they imaged part of the planet that had never been seen before. Talk about a career high. That was amazing. The same day, the NSF contracts officer called and said, we don't allow fee for engineering services on contracts for engineering services, and more than half of the Ampere proposal was to pay Boeing to implement Ampere, okay? And so who seriously thinks Boeing is going to say, oh, well, we don't need to make a profit and set a precedent on this little teeny project? Not a prayer. So that was that day. What a wonderful day. So anyway, we spent some time working with Iridium, and this is how it actually happened. In April, we had a call between the head of contracts at APL and the number 2 at NSF, okay? And one level below the director. And they said, we had about a 30-minute call, and at the end of that call, they said, well, I'm sorry, but we won't be able to do this. And then I said, before he hung up, I said, what if we just purchased the data? And he said, you mean there would not be a subcontract for engineering services? There's a legal, it's legal stuff here, right? Correct, just a purchase of data. Well, as long as you can demonstrate the price is fair and reasonable, that'll be fine. Then I said, okay, how soon can we send you a revised cost proposal? We restructured the subcontract as a data buy. We set the price below what it would cost to just send the data over the network. It's the same data, same value, actually, to Iridium. And then we rewrote the contract. Literally, I just deleted that and wrote that. That's really what happened. And then Ampere actually started on the 1st of January 2010. That's where data is available. You go to the Ampere server, it will be there. And next is now. They're launching the replacement satellites. 30 are already up. The next 10 go up on the 22nd of December. We are working with that data. It's great data. There's some noise in it, and we're cleaning it up, okay? So that's why I had to pause the process and the products that are coming out midsummer. I had to pause it because half of our constellation went away and the inversions just flopped. But the data's there. I just have to put the processing in place to get there. We're getting there. So there's a little pause. So relationships first. Build trust with your sponsor and your partner. Listen, understand, communicate, and be straight. Oh, did I say respect? And see it from the commercial side. Economy matters. They're not going to lose money doing something for you. But they aren't necessarily going to need to make as much money as they do on other things, because don't undersell the science. The engineers and the executives get a kick out of the fact that they're doing science. The Iridium people really do find this stuff interesting. They won't lose money to do it, but it's cool. They can be pulling for you, like they did. It was the engineer who said to me, we could just do a data buy. That came from them. It wasn't my innovation. So if you respect them and you treat them like colleagues and equals, you can really be a partner. So that's where it starts. And that's all I had to say. Thank you.
Thanks, Brian. That was great. Time for a quick question or comment? It was great. I think I knew that, but that you have to frame it as a data buy, but that was really useful probably for a lot of people. There's probably a lot of creative ways to think about that.
Yeah. Now, it may be that Iridium would have done that back in '99 to get around their problem, but they saw the bankruptcy clouds on the horizon, and frankly, I just think they weren't motivated to try to find a solution because they had bigger problems. I think Rob Pfaff has a question.
Yeah, I've said this in previous meetings. I just want to say again that, Brian, I think you should be congratulated for this entire effort. It's really fantastic. And my question is, for Iridium Next, were you able to get the higher sensitivity? better than Tesla and all that?
Nope. That was a classic. I was talking with them about that, and they said, yeah, we've talked with our spacecraft providers. The problem is the MAG is embedded in a flight heritage system, okay, which is part of their control system. And they did come back and they looked at it and they said, yeah, we can do that. Can you get us $2 million in 6 weeks? That's what I mean about the disparity between the commercial timeline and the acquisition timeline that we have. But it turns out the resolution of the data, the net performance is going to be about a factor of 3 better than what we have now.
Okay, thanks very much. We're going to move on now. We're only about 5 minutes behind, which isn't too bad. We're going to hear from Liz MacDonald, who's going to talk about the spark of disruptive innovation for space physics and aeronomy.
All right, thank you. This talk, I appreciate the opportunity to speak freely here, and I recognize that I have a privileged, kind of secure position, secure job, and I hope that we can create more opportunities to continue this discussion and hear from a wide variety of people in the future as well. That said, this also kind of follows on from a few of the previous talks, and you'll see those threads, like Larry and Allison were definitely on the same wavelength. And this is a talk about big ideas. So they may not all connect with all of you, and that's okay, but I hope that some of them connect with some of you. So this is inspired by a recent class that I took actually on leading innovation with business leaders. And it's also by my experience leading and founding the Aurorasaurus project, which is the first citizen science project to report auroras in our modern app-enabled era. So that experience informs this. Okay, and so the structure of the talk, I will define disruptive innovation, talk about some examples, and what this means for our field in terms of opportunities. I think we have lots of opportunities to be innovative, and some of those are really at the interdisciplinary areas as well. So, oh yeah, and then before I move on, I'll say that I've also bought data in the form of tweets. And I could tell the same similar story that was just told, but different customers, so, okay. Whoops. What did I do? Okay, thanks. Okay, so disruptive innovation, this is kind of a hokey plot from Wikipedia, but you get the idea that the axes are performance and time, and the non-linear line there rising, starting from a very low performance and then eventually rising faster than how most of our technology rises as we continue to refine it. That's what disruptive innovation is to me. People who study this, it tends to come from the outside. It doesn't come from all of the usual kinds of methods. It also requires both the idea and actually the execution of the idea, which is all of the persistence that was just spoken about. And there are different metrics for this as well. It looks a lot different than what most of us are familiar with. And if we think about what this looks like Phil talked about, 20 years ago, what technologies would you have picked out that we would still be using, right? And it's really hard to do that. And you have to look for kind of weak signals. It's very hard to know what those are going to be. So I will get back to that. First, I'll talk about more, some of the examples. So building a Cubesat here. These are high schoolers building a Cubesat. And so people might look at this picture and some might see a great educational opportunity, really game-changing access for a lot of people to work on hardware and get excited about that. Some of you might be looking at that and thinking about space junk. And that's okay, actually. That's kind of what disruptive innovation does. It has a wide range of performance. So something that makes us uncomfortable, that we're maybe not sure about at first, can also be something that is very, leads to the high quality science that we're looking for as well. So that's really where CubeSats have gone. Since the late 90s, started in Cal Poly and with Bob Twiggs, The innovation, if you ask me, is really the P-pod itself, which is the way that these very small satellites are launched in the excess lift capacity of larger rockets. So now, more than 500 of them have actually been launched, and the success rate is climbing. But certainly if you look at the first several years, they were not successful in terms of getting data back and all of that. And I also want to give a shout out to Therese Moretto-Jorgensen at NSF, who was at NSF, for funding the science that can be done in our field with this new technology. So she really recognized that and enabled that. And NASA is now, fully on board with Cubesats as well, and also with how we can enable constellations, explorer programs, missions of opportunity, and much bigger science with that. And also recognizing that there are different metrics in terms of quality assurance that are needed for the different sizes of programs. So you can see the establishment has adopted Cubesats. The images here are from the United Launch Alliance and the National Academies, which just recently did a study on Cubesats and also mentions disruptive innovation in that study as well. So, okay, next example. So this is the project that I lead, and what it has to do with is, we are starved for data. We can't actually tell you when and where the aurora can be visible, and so this project was aimed at improving knowledge of where the aurora was visible for the public and also for science use. And then it's not something that has existed before, so it's also difficult to know how to define it and to really take a risk with that. I've definitely been told, this is just education. It's not just education. We have a lot of papers on the scientific use of people reporting that they can see aurora in real time as well. And also I've been told from people outside our field that I'm trying to communicate with the public about how you do this and what the aurora is, and literally everything I'm saying is total jargon. And we need to recognize that as well. We need to, stretch ourselves to figure out how can you, where are you going, and how do you need to adapt to get there. Let's see. So the data that we take are lower quality, but there are so many very smart people out there who are so interested in our science. And so this was really about enabling a pathway of connecting with those people and changing the way that we do that outreach as well. So there are more projects like this now involving citizen science, the ham radio project, HamSci, and also the Citizen Cape project, for instance, which recently during the eclipse gave all these teams professional telescopes to take observations of the corona. Really different new ways of getting data that we haven't done before. So one result from our project is actually the discovery of something kind of called the Steve Aurora. So we have been, basically people noticed something that we, the scientists, were not noticing, and they brought it to our attention, and we've worked together with them to understand more about what this is. And so this is an arc that's a subauroral arc, and people were out during storms, and they noticed this, and they said, what is that? It kind of had they called it a proton arc. Eric Donovan said, no, that's not proton aurora. And, they said, okay, all right, well, we're going to call it Steve, and we're going to keep taking some observations. And this is a time lapse of some of those observations that really show optical phenomena that we haven't seen described before. And we now have a swarm conjunction with this event, and we can place it in much better context, geophysical context. And it may turn out to be one of the most broadly visible types of aurora because it's occurring over lower latitudes where more people can see it, which is really cool. It may also turn out to get us to question what we actually call aurora and refine that definition. So if you want to hear more about that, I have a talk tomorrow on that. Okay, so now I'm going to kind of broaden this back out to the theory of innovation. And this figure comes from a book called The Three-Box Solution by a business professor at Dartmouth College, Professor Vijay Govindarajan. And basically what he's saying is that it's very simple. There's the first box, which is managing the present business. And that's the dominant logic of your field. That's the performance engine that's getting all the science and the satellites done. In that area, we want to do that as well as we can. And that's also very risk averse because risk is a threat to the performance engine. So he also defines two other boxes. The third box, which is creating the future, seeing 20 years into the future by analyzing these weak, clunky signals. And he says that you really need a different team to do that. You can't just take the people from the performance engine. You need people who have the freedom and the creative vision to be looking there. And also, in order to do that, you need to forget some elements of the past, and you need to look at what those elements are. And so, in our field, I'm just going to throw out a couple ideas for this long-range thinking. What if we forgot failure is not an option? NASA's previous slogan. What if we forgot the constraints of the current decadal survey and where that's going in the next 10 years? Or what if we forgot the glory days of this is how it was when I was a student, therefore this is how it should be now. So, I think we need to look at some of these things in order to move forward. So that's the last slide that I have here is that we need to prioritize and do more of this box 2 and box 3 thinking. Planetary is already thinking about what are they going to be doing in 2050. We should definitely be figuring out what's the time frame and what are we going to be doing, and how can space physics and aeronomy get there, and what does that future look like. And I would also suggest that in order to do that, that we really want to be inclusive and to, that we are not currently getting ideas from all people, and we do have a broad range of people here. And so we really want to expand that, and that, if you're doing this and thinking about the future and you're really comfortable doing that, you're not doing it right. So you should really be uncomfortable and pushing forward. And I think that having a broad range of opinions is critical to that. So that's it. Thank you.
Any questions or comments?
Really? Why Steve?
Steve is a Canadian kids movie, and there's this creature over the fence that they don't know what it is. It's an animated film, and they say, "What's that? We're afraid of that." And so don't be afraid of that, just call it Steve. It's like an animated dog or something. So I don't know, it's just a fun name, and there's really fun groups of people out there who are contributing to our field, and I'm really grateful for those folks as well.
Great. Thank you, Liz.
Hey, are we up there? Oh, this one, sorry. All right, so next we're going to hear from Jared Espley. He's going to tell us something about planetary smallsat missions. So I think you want to use this.
Okay, great, thanks. Yeah, thanks for having me here. What I wanted to do is I wanted to use the theme of our session of future innovations in space physics and try and apply those to planetary missions and some of the really exciting opportunities that we have to do innovative work with space physics at targets throughout the solar system. Okay, so here's my summary, take-home message. These are things I want you to know. So for small sets, there are lots and lots of opportunities to get into near-Earth space. This is not news, perhaps, but it's an important part. Small sat missions can then travel to planetary targets from near-Earth space. This is something that's only come to the forefront recently, and we're on the cusp of actually technologically being able to do this. And therefore, because of that, we can do world-class space physics missions via small sats because we have the instrumentation to fit on board of small sats. So there will be lots and lots of opportunities to do this in the very near future, in my opinion. Okay, so let me just very briefly walk you through all the different elements of this. Some of this will be repetition for many of you. I'm basically talking to myself about a year or two ago, what I knew a year or two ago. So there are many, many launches that have lots of excess capability. And what I mean by capability is volume and mass. And this, of course, happens because you have to buy a whole, your launch vehicle has a finite number and your payload has to fit into that. And by rounding, there's always excess. And by excess, what we really mean is volume. You can see Discover physically is teeny tiny inside the fairing of its Falcon 9. So there's an excess of volume, but also perhaps even more importantly, excess of mass. And of course, so then there's oftentimes thousands of kilograms of excess capability, and sometimes it's just tens of kilograms. Okay, so once we have excess capability, how do we actually get our secondary payloads into space? The most well-known way, of course, is CubeSats. To use CubeSats, we have CubeSat deployers. So these are typically going to have a standard size and standard packaging. They have to literally be boxes, typically, to fit into those deployers, and then they're deployed through various standardized ways into, like from the ISS, that's Dellinger on the right there, that was just deployed last month, rather. Another way that's really exciting that many of you will know about already are the SPA rings. This is the secondary payload attachment ring that allows then a variety of payloads to be attached. And so basically these rings are standardized commercial products that can then be attached to the launch vehicles, attached to the primaries, and they have 6 ports on board typically, and each of those ports can carry up to 180 kilograms, and they're not at all fixed in the box the way a CubeSat is. You can have a very diverse set of payloads that are attached so long as they all fit within the volume and the mass that is required. And so what that means is that you can have a very wide variety of the types of material and payloads that can be carried. You could even have whole arrays of CubeSats with their deployers on board. You can see an example of that one on the right with a whole bunch of CubeSats in their deployers attached onto those SPA rings. Okay, so everything I've told you so far applies to everything you would have known about already about the opportunities to do space physics at terrestrial, for terrestrial missions. You get into space, you do your space plasma physics. What I want to tell you about is how we can go to other targets throughout the solar system. So the way we do this is by using the, typically would be attaching ourselves, again, with an SPA ring, for example. We're attached to the primary payload, which again has already spent its $100 million to get its launch vehicle into space, so somebody might as well take advantage of it, and that'll be us with our secondary payloads. The important part that happens is the upper stage places that primary wherever it's going to go, and then typically the upper stage, or in many cases, the upper stage can then be driven into heliocentric orbit to get away from the space debris problem. They want to send it away so that the upper stage is not going to be a space debris problem. And so when that happens, then that of course can put our secondary payloads into heliocentric orbit. And when that happens, then we have the opportunity to detach from our SPA rings and our little spacecraft can go flying off to their individual targets. Now, this is somewhat this type of mission scenario that I'm describing could also be applied to payloads that are going directly to a planetary target. So for example, Mars 2020, would be going directly to Mars with its primary. But in that case, what we'd want to do is we'd want to detach our secondary payload at Earth, just like the scenario I'm describing here, because what we would need to do is we would need to slow down enough of our small satellites in order to be able to go into orbit at Mars. So I'm basically describing all possible scenarios where we could take the secondary payloads and get into planetary targets from near Earth space. Okay, so this is a busy diagram, so I'm going to spend a couple minutes walking us through this. This is basically a whole bunch of trajectories that our flight navigation colleagues of mine at Goddard helped us work through. This is describing the scenario that I was just saying, where we have a secondary payload that's been a part of an ESPA ring. It's detaching in heliocentric orbit, and the first assumption is that we're being boosted into heliocentric orbit with quite a bit of momentum. This is not unrealistic because lots of times the whole launch vehicle itself has excess momentum, and so they have a little more rocket fuel on the second stage, the upper stage, to give us a little extra kick. Technically, this is a C3 of 13 square kilometers per square second is the way the flight navigation people describe it. So C3 of 13. We're going to use solar electric propulsion, and we're going to try and define flight times of less than 3 years to get us to the target, which in this case was Mars. Okay, so with those assumptions in mind, then what we have on the y-axis is the mass of the delivered dry payload. So this is after all the rocket fuel has been expended on board the secondary, versus the launch time. And then each one of those dots is a particular trajectory. So there are literally hundreds of trajectories that the navigation people have put together here, and you can see several patterns already. So some of those patterns immediately, as you can see that there are certain times when it's easier to get to Mars. This is not news. It's easier to get there when the planets are lined up properly for the trajectories. One of the other things, though, is that it's not a really, really tight launch window like lots of times it is for planetary missions. Lots of times the planetary missions have very narrow launch windows. Because we're using solar electric propulsion, it's a very broad time where our spacecraft are able to traverse interplanetary space. So it's many months of launch window. So if there's a launch with an appropriate mass excess, with an appropriate C3 heliocentric delivery capability, we can take advantage of those launches, even if they're not planetary launches. Then the other really interesting thing is you can see we can get up to approximately 30 kilograms of dry mass being delivered to Mars. And so this is a really opens it up for a truly innovative, true small sat level spacecraft to travel to different planets. Okay, so once we get to any of these targets, what type of space physics would we like to do? Obviously, we have lots of other colleagues in planetary science, but we're here in this room, myself included, we're interested in space physics.
Sorry.
Nope, did we switch over?
No, you're right here.
Okay. Okay. See if I can make it full screen. Let's click through my slides real quick. Okay, space physics. Lots of interesting things to do besides all the space physics that many of us are interested in at the Earth. There are many things throughout the solar system, the Venusian magnetosphere, cometary reconnection through their tails, the Jovian auroral physics, which is going on in a Juno session right now, space weathering of the lunar crustal fields. It's been worked on by many colleagues here in the room. But the one that I really wanted to emphasize today was the exploring Mars's induced hybrid magnetosphere. And so what I mean by that is, as you probably know, Mars does not have an intrinsic dipole planetary magnetic field. And so instead, the solar wind interacts directly with the ionosphere and also with the patchy crustal magnetic fields that are at Mars. And as those patchy crustal magnetic fields rotate in and out of contact with the solar wind, we end up with a time variable magnetosphere, induced magnetosphere. So you have time variable dynamics of the magnetosphere, you end up with time variable ionospheric currents, you end up with time variable reconnection as the mini magnetospheres of the crustal fields interact with the solar wind. And so it becomes a fantastic dynamic plasma laboratory to really try and understand how magnetospheres work in a variety of ways. So, because this is such an interesting place to go, there's a variety of mission concept studies that are being considered right now by a variety of teams. There's the MarsCat proposal that's led by Edgar Bering out at University of Houston. There's the MESON mission concept led by Rob Lillis out of UC Berkeley. And there's the M4 concept that I'm leading at Goddard. These all have the same basic idea to explore the space physics of the Mars-induced magnetosphere and to try and understand those dynamic time variable things that are happening with at least two spacecraft, the multi-point that so often we want to do with space physics here at Earth. We want to extend that to other objects. So how can we do that? We do that with world-class space plasma physics or space physics instruments. I'll emphasize our magnetometer because that's the group that I'm in, but there's a wide variety of different space physics instruments that are widely available, that are cutting-edge, world-class, that can be put onto these spacecraft, these small spacecraft. So in our case, for the magnetometer, we would probably emphasize, instead of our standard mag, which are comparatively small already, we would go even farther down to what we're calling our mini mag, which flew in the 90s on a mission on polar orbiting geomagnetic survey. It gets down to 40 grams, and it gives us world-class science measurements down to 1/10th of a nanotesla. And so there are many other such missions, like I said, ion spectrometers, or many such other instruments, ion spectrometers, like E-field measurements, other magnetometers. I'm biased towards ours, but there are many such instruments, and these are the engines that let us do world-class space physics at planetary objects by putting them onto small sats. Okay, so in conclusion, I'll just go back to the take-home message. We've got lots and lots of opportunities to get small sats into space. Once they get into space, we have the technology now to just barely start to make the real mission concepts to travel to other objects throughout the solar system. And when we get there, our field is probably one of the best fields to take advantage of that. There's lots of innovative things to do, interesting planetary surface studies, but our field of space physics is ready to take advantage because we can go into orbit with our world-class instruments at these other objects and do space physics there at these other objects. Thank you very much.
Question?
How do you do the orbit insertion at Mars?
So in the mission scenario that we're talking about for going to Mars, how do we do the orbit insertion at Mars? Again, using solar electric propulsion, you're able to spiral down very gradually. So with the amount of momentum that we would have as we're approaching the planet, we'd be able to capture into a very elliptical orbit because we would just be barely bound by Mars and gradually spiral our way down over a matter of months with a very low thrust but continuously available solar electric propulsion.
Okay, yeah, one more.
Yeah, the link margins are going to be very small for communication. So what is your expectation for communicating your physics back, and what's your opinion on, for example, laser communications?
Okay. Yeah, so the question is, how do we get our data back from these planetary objects because they're so far away? Two ways. The Deep Space Network can communicate with some of these small sats with the current technologies. The IRIS radio that JPL has put together, there's one from Tethers Unlimited that has the communication capability even at opposition, so to be able to communicate some data. There's also satellites in orbit at Mars, for example, that would be able to do relay, and so that's a way we would get a lot of our data back. I personally have no technical expertise on laser communication, so I can't tell you anything about that. Sorry.
All right, thanks very much. All right, we're going to move on to our next speaker, which is Trey Winter, who's going to tell us about Icarus Investigations, a model for engaging citizen scientists.
So thank you very much for inviting me to talk at this.
Keyboard.
Okay, great. First of all, I'm going to say that this is not the most innovative work that I've done. I think it will be, but we had a lot of talk about inclusion today in several of the talks. And I just want to give a shout out to my other talk. There is one group that is the most excluded from astronomy, astrophysics, and space science, and that's people who are blind and visually impaired. And they can actually be an active part of not only joining with us in space exploration, but actually doing that exploration as well. So if you're interested in including that one group, then please come see my talk in the education section on Wednesday. All right, so with that advertisement out, Icarus Investigations. So what I want to talk to you about is something that probably shouldn't be innovative, but it is. And this is something that Liz knows all too well. And that's actually getting the public not only excited about what we're doing in space exploration, but getting them to be part of the process of exploring space with us. And that's what Icarus Investigations is all about. I'm Trey Winter. This was partially my idea that I've been wanting to play around with for a while. But Caitlin Loftus, who's in the back, she just got accepted to Harvard Graduate School, and she's the one that's actually did all the hard work for this, and she deserves almost all of the credit for this. So thank you, Caitlin, and thank you, Lockheed Martin, for supporting this work through the AIA subcontract. All right, so I say the sun. I'm not a space physicist, I'm a solar astrophysicist, but we work together on things, so I get to talk here anyway. And if you're not familiar with solar physics, it is the best field of physics to be in. Why is that? Well, it's many reasons, but one of them is that we've got one of the best imagers available, the Atmospheric Imaging Assembly, or AIA. AIA takes images in the sun from white light images to UV images to extreme ultraviolet images. And it produces some of the most fantastical images of space that there are. I call it the Hubble for solar physics because we are just that good, and I really don't have much shame, so I get to brag. But we have some challenges with this AIA data set. First off is that we take about 8 images every 12 seconds. Well, that doesn't sound so bad until you realize that our detectors are 4K by 4K. So if you've got a 4K TV screen and you think you're fancy, no, not really, because actually our images are about twice as good as that because they're only 4K in one dimension, not two. So we have over 16 million pixels of data that we take for each image. So when the spacecraft is pretty smart, it uses Rice compression to compress that down to 1.5 terabytes of data a day. They go to a special downlink center. But once you do the process, expand it, do the processing, add those nifty colors to it, all of a sudden you're dealing with about 3 terabytes of data a day. That is a lot to go through. I don't know about you guys, but when I was a graduate student, I was like locked in the basement sifting through data to try to find the interesting stuff. With 3 terabytes of data a day, you cannot do that. There is just not enough Mountain Dew produced to keep the graduate students going in order to sort through that kind of data flow. So we've got to come up with different systems. And the mission launched in February of 2010. And we currently have over 6 petabytes of data to go through. So it's like, oh, I saw this one neat thing that one time. I wonder if it's ever been on the sun before. You've got 6 petabytes of data to go through. That's a lot. So how do you do that? There are lots of technical challenges. And when you've got that much data, there are technical challenges to actually touching that much data. And honestly, the technical challenge is how do we pay for it? The AIA mission went under a budget cut. And so, you know, a lot of this information is getting to be hard to access. So how do you get to the data that you want, that you need as a scientist? And that is a key thing that we're working on. So the thing that I work on primarily are solar flares. So that's what we're going to be talking about primarily. And if you look at this little region that we're zooming in on, that is a big, beautiful solar flare. There's a flare underneath it, and then we have this eruption of material. You have beautiful things going up off the sun and then falling back, causing all these beautiful secondary explosions. And this is what we typically think about when we think about a flare. However, this is one of the rarer types of flares. This is what we call an X flare. And so an X flare is actually, if you were to scale and rank flares, X is at the top of that list. But flares, if you count how many flares of what different type actually go off, X flares are rare. And there are many other types of flares that aren't quite so energetic. They go off all the time. And there's a lot of scientific questions about those kinds of flares. Are they of the same type of these bigger flares? Or are they different not only in size but of kind? And we don't really study those smaller flares as much for several reasons. We just have an investigative bias towards these bigger flares, the X and the M flares. And that's because they're sexy, right? They're the big explosions. They give off more energy than the entire world will use in 100,000 years. And they give off that amount of energy in about 10 to 15 minutes, right? That's kind of big stuff. That's stuff you can get in the newspaper. But these other smaller flares, the C flares, the B flares, even the tiny A flares can tell us a lot about how the sun works that we don't understand. The problem is that even though they are more numerous, the data becomes far more complicated for these flares because they become part of the background. Another complicating factor is that flares occur in every different wavelength you can imagine, from radio to X-ray to sometimes even gamma rays. And so trying to determine what features of a flare in one wavelength correspond to another feature in another wavelength of the same flare is sometimes hard to parse out. So how do you do that? And one of the main challenges is that we did actually think about this ahead of time. We did think about how do we sift through this much data? How do we collect a lot of metadata on the data, right? So, trying to take these big, beautiful images and movies that we have and to collapse them into some squiggly line plots and graphs and, some kind of more concise database. That's called the Heliophysics Event Knowledge Base, or the HEC. And there were several people that made automatic routines to try to detect features in the solar data in this fire hose of 3 terabytes of data a day and try to put it into a more concise form. I joined the project late and, well, maybe didn't quite bungle it, but there's a flare detective module in there that is supposed to detect all the flares that go off in the sun, large and small, and characterize them. And the problem is that the project ran out of money before we did the most critical part of any project, and that's data validation, right? So we came up with some theories, we came up with how to structure it, how to make these things work based on our past instruments, and then tried to fit it into this new instrument, and then we let it go, and there was never any going back and seeing how well we did. And when we had a very talented research experiences for undergraduate student named Caitlin Loftus go through the database and try to find flares, she would come back to me and ask me often, well, why is there not really a flare here? Or why are these start times and end times slightly off? Why is the data kind of wrong? It's making it hard to do my science. And that's what we're trying to do here. We're trying to go back and do a lot of data validation as well as make new methods for detecting flares, right? So how do we address all these when we have no funding for this kind of data validation? Well, we look to other places where we can actually fund some of these efforts. And one place that we can find maybe some funding is education public outreach. I know, right? There's usually no money for education public outreach. But we can actually do a little bit of magic by getting education public outreach and science to work together. And when we have all these challenges and we're dealing with big data and we're dealing with parsing through 6 petabytes of data, we're not going to do it just by having graduate students look through the data. We're going to call in the robots, all right? And this whole project is based around machine learning algorithms. And if my career is defined by anything, it's by basically hacking industry technology and trying to find ways to make it work for science. I was working with GPUs back before people were knowing how to do it, before it became commonplace. And that was because the video gaming industry's annual revenue is 5 times that of the NASA budget. And they put about 1 NASA budget per year into R&D. The machine learning algorithms that we want to go through and actually sort through the 6 petabytes of data are actually the exact same machine learning algorithms that puts that exact right picture of a kitten in front of your face for clickbait. There's actually been many millions of dollars of research going into primarily image recognition, but now video recognition algorithms. Very little of that has actually been from the science side. It's been driven by the business side. But basically, as we were talking about earlier, as our budget budget DT goes down because the industry budget DT goes up, we lose that talent to places like Google, but they started wanting to be us, right? And so they like to play with us and try to do science again. So it's pretty easy to get some of these people who are very well-versed in machine learning algorithms to work with us. So they can work on large data sets efficiently. They're effective at handling complicated data sets, but the problem with them, especially the ones that we want to use, is that they have to be trained. You have to tell the robot, the machine learning algorithm, when you get it right, when you get it wrong, right? And this is where the citizen science and the education public outreach comes in. Because we can actually leverage our instructing people, the general public, on what flares are and how science works into actually training these machine learning algorithms and get a twofer. And actually we're going to get a threefer, because not only are we going to teach the public about what flares are and use that to train the machine learning robots, but we're going to go back and use my broken heliophysics event knowledge base HEC data set as the first case, and fix up the database at the same time that we make these new methods. So basically what we're trying to do is to hit 3 different birds with a single stone, to use a violent metaphor. All right, so the big idea behind Icarus Investigations is to use the Zooniverse.org framework. Zooniverse, if you haven't heard of it before, is a citizen science project. They started off with the Galaxy Zoo, and it has grown and grown and grown. It is the premier platform for doing citizen science type platforms. We're using it so that we don't have to reinvent every wheel, and that we can use the knowledge that they have built up over several years. The last estimate that I have, they have over 1 million people actively working on science projects. Not scientists, not people like you and me, but just members of the general public who are interested in science, who are excited about science, that want to participate in real results, right, in generating real results. And so we plan to leverage some fraction of those people to go through and look at our data sets and determine different aspects of the flare, all right? And we do this using video game metaphors. So we start the training off, and as you learn more and you get better and better, you end up leveling up, right? So you get experience points. And one of the things that we're trying to do is not making it competitive between people, but make it so that it's you are constantly working to better yourself in the score. And this is very important. If you look at the research, there's not only a lot of scientific, hard science research, but there's a lot of sociological research that goes into the making of these projects, and it's all available to you if you start to use it. And I need to kind of hurry up because I went on a little quickly. So, this is the holy grail. We're using EPO and science together. And just to give you a quick look at a framework, this is what our Zooniverse framework looks like. You can learn more about the flares, get trained up on how to identify different aspects of the flare. And we've made a lot of progress with very little money. We have a tested Zooniverse interface and workflow. We've defined a machine learning algorithm for testing it. And we're finishing up the workflow to verify the previous flares in the HEC. And we're working on a proposal to expand the project. This image I've gotten here is not of a solar flare, but it's of a filament eruption, and the whole idea behind the Icarus Investigations is to start off on flares, but to make it an extensible framework so that any solar physicist can use it. If you're interested in any kind of different phenomena on the sun, we already have volunteers that are familiar with solar physics with the framework, and you can utilize that framework for your own project. And with that, I'm over time, so I'll just take questions and comments if we've got any time.
Yeah, time for a question or a comment. Is anything out there? Yeah.
Just a quick comment. There's a company called CCP out of Iceland who developed a game called EVE Online, and they've actually, inside the game itself, embedded a way for the player to identify exoplanets. So, yeah, so maybe not even going through like a nonprofit organization, but through a for-profit developer directly to try to do science inside of the video game.
Yeah, I've worked with a couple. So, the suggestion was maybe work with a video game developer like the makers of EVE Online. I will say that I've had a good experience working with NVIDIA Corporation, doing some of these projects, and Google. But I do think that there's a lot to be said for working with for-profit companies. But as we've heard before, when you're in the framework of an educator and working for a nonprofit on Smithsonian, you do have to think about a lot of these legal things. And also, too, I do want to make sure that we do science that's available to everyone, not just paid subscribers. But it's still a great idea.
All right. Yeah, thanks very much, Trey. Next, 2 talks left. The next one is we're going to hear from Jacob Bortnik, who's going to tell us about virtual space, the vision of a machine-learned virtual space environment. Jacob.
Thanks. Keys. Does the mouse work as well?
Mouse works. I think this is what you want.
Okay. Forward key. All right. Good afternoon, everyone. The title of my talk is kind of a spacey, futuristic-sounding virtual space environment. Okay, this is a vision of how we're going to use machine learning technology to create something that is a virtual environment, something you can interact with and fly through. Just to set the scene and kind of frame my talk, I wanted to just go back to the description of this session. Now, we were told to give TED-style talks, grand, forward thinking. So just to read the first line, our field is poised to make a leap forward by being able to take advantage of new technologies. Right in the middle there, disruptive innovation is critical, but it's sometimes not prioritized. In fact, you often find, like in Brian Anderson's talk, that much of the innovation was actually done offline before it was even sponsored. Right? The innovation started earlier than the funding and the big interest. Right? We need to exploit new ideas. Last line there is, how do we evolve beyond current traditional methods in order to innovate into the future? And that essentially frames my talk. I'll tell you what we're doing now. I'll tell you what we should be doing, or at least what I think we should be doing. And I'll tell you what we could be doing right now with our current resources, our current data, our current capabilities, something that Terry Onsager was asking. Well, we have all this data. What do we do with it that's a little bit clearer than what we're doing right now? So, what are we doing right now? This is what it is. So I've shown you a picture here. I've shown you two pictures. Top left there is by a friend and colleague of mine that I work with quite frequently. He wrote a paper in 2002. It was a very nice paper. He just took some data from a satellite and he plotted it. There's a function of L shell and MLT. That's the top left. I can't actually point you because I don't have a pointer. Do I have a pointer? No. I don't have a pointer. That's fine. I can do the mouse.
No, it's this mouse.
Okay, that's fine. That's fine. You guys know where top left is. So in the top left, the author plotted this dial plot. It was satellite data. It was 2002, and it was very nice, and it really told us a lot about what we wanted to understand with that data set. This is plasma waves. It's what we call whistle mode chorus waves, for those who are not familiar with it. But the point is, fast forward 10 years to 2012, same author et al., and I'm not putting his name down, not because I don't know it, but because I don't want to embarrass him. He's a good friend. This is not something against his science. So the same author et al. Plotted essentially the same plot 10 years down the line with something like 100 times more data. The volume of data has grown by a factor of 100, right? You see now, instead of just CRESS, we have DE1, CRESS, cluster, TC1, Themis, roughly 100 times more data. And what do the plots look like? Do they look 100 times better? Well, they do look a little better, but I wouldn't say 100 times. And so you'd think, well, I don't know that our methods are really accommodating all this extra data that we have. Here's top left again. This is a different kind of wave. Now this is 2004, same author, and right now in this very day I'm supposed to be reading a manuscript that I'm a co-author on that essentially plots the same information, and now there's more than 100 times more data. Right? We're more than a decade down the line, and currently we're doing the same thing with it. So this is what we're currently doing, even though the data volumes are growing substantially. Right? So that's kind of an issue. So let's just go ahead and extrapolate this forward. So we got 100 times more data over a decade. We're probably going to do the same kind of growth, you might imagine. Here in the top right, you see some data volumes. These are just solar projects. So you see the SDO in the light blue curve there between 2010, 2020 is roughly on the order of a petabyte. Okay, petabyte is 1,000 terabytes. It's growing. It's going to go into several petabytes. The larger solar telescopes are going to go in 2030 to tens of petabytes. Okay, so data growth, of course, it's huge. It's exponential if you see it on an exponential curve there. Bottom right is Earth science data, same kind of thing, exponential data growth. And just to frame it again, I've given you some typical data volumes. So web pages are about 10 petabytes. Right? YouTube uploads, now the rate is YouTube goes at about 2.5 petabytes per year. So that data is increasing substantially. Large Hadron Collider is giving you tens of petabytes. Radiology, interestingly enough, high-res images is a very big data source. And now back to science, the Large Synoptic Survey Telescope, just kind of a fantastic project that's going to map out the night sky, look for all sorts of amazing effects. That gives us about 15 terabytes per night, right? The square kilometer array that I know a little bit about because it's half in South Africa and half in Australia, it's threatening to give us a petabyte per minute. It's going to be the sort of granddaddy of data volumes. So, you do the multiplication, it's something like 5,000 petabytes a year. That's wonderful, but, we know what the normal approach is to analyzing data right now. We go to a website and we download it to our computers and then we look at it. And we won't be able to do that with, 5,000 petabytes of data. We're just not going to be able to do the same thing we're doing with the kind of data that we're going to be getting, and we're already getting, right? So the normal approach to just downloading data, that's just not going to last for very much longer. What about space science data? I think we're actually in the same boat. If you take a look at the Heliophysics System Observatory, it looks very different to what it did 30 years ago, right? And that's not even complete. I mean, that's not showing you a lot of the low Earth orbiting missions. I don't even see Ampere up there. So, that's sort of an underestimate, but heliophysics space is getting populated. The data volumes are growing. The top left panel shows you how much data the Space Physics Data Facility is serving on a monthly basis. And I've quoted some numbers there. They're a little old. So as of February of 2016, SPDF had something like 91 terabytes of holdings from 23 spacecraft, something like 6 terabytes are served per day, but that's sort of below, before RBSP was even added to it, and it's before MMS was added to it, before Cluster was added to it. And so data volumes are growing. Okay, here again is a graph of this exponential growth. And if you sort of do the rough math, it's something like a factor of 2 growth every 2 years. So obviously you'd heard about Moore's law from somewhere. So, data volumes are growing. What we're doing is not particularly growing. So the question is, what should we be doing? And so here comes just a few of my own thoughts. So the first thing is, what should we be doing? The first thing we should be doing is we should be figuring out, this is in accordance with Terry's question, we should be figuring out how to exploit archived data. We have all this data that is in archives. It's available, it's not going to go anywhere. How do we use it? I mean, part of the problem is when you look at an event right now, which is exciting, it's something that we're all talking about. Let's say there's a challenge on a particular event. We can't use all that archived data, right? It's just kind of stored there. So it's not maybe relevant to what's happening right now. And secondly, in the blue there, we want to make sense of large and increasing volumes of data. I've shown you my little scary exponential growths of how data goes. We want to be able to figure out methods of how we boil down those terabytes of data into something that is insightful, that allows us to understand the system, right? Petabytes of data just can't be visualized in the normal way that we do right now. The second thing is, or the third thing is, we want a model that improves as data is added. This is a critical component. So what I showed you in the second and third slides is a model that doesn't improve as data is added. It's a model that kind of saturates pretty quickly, right? If we 10-fold, 100-fold, 1,000-fold the amount of data that goes into those dial plots, we're still going to get pretty similar looking dial plots. We want a method that is like Google Maps, right? You click on the map and you see something that's kind of blocky looking, and then you wait a few seconds and the blocks get smaller and smaller, and then you wait a few more seconds and the blocks get, beautiful and high res, and you can zoom into it and you can suddenly see houses and cars and people and things. That's what you want your model to do. You add more data, you get a better model, more resolution. So that's point number 3. Point number 4 is kind of subtle, but this is just my opinion, but I think that in the era of distributed arrays, we're treating an array of spacecraft as a bunch of individual spacecraft. I just don't think we're doing enough of coordinated measurements, right? We're doing some, I'll give that to the community, but we don't have a good way to take into account all these coordinated observations and do something meaningful with the coordination specifically. And coordinated arrays, distributed arrays, are something that's only going to grow. And so I'd like to propose a method that takes full advantage of coordinated, simultaneous, high-resolution measurements. So that is what I think we should be doing. And now to the good news, or what I think is good news. What could we be doing? So here's my one suggestion. So I've been thinking about this for a number of years, wrote a little paper on it in 2016, listed in the bottom right there. But the idea is we have satellites that go along their orbit tracks and they measure some quantity of data. You can imagine what your favorite quantity is, let's say number density. And it's measuring a number density every so often at a single point over a very long period of time. What you want is you want the opposite thing. You want one point in time, but all points in space, right? You want a 3D model at a particular time, and ideally you'd like to advance time and see how your model dynamically evolves. You want to kind of map from single point, lots of time, to single point in time, lots of space, and something that is dynamic. And so it turns out that you can take satellite data, the sort of time series of data, the location of the satellite, a good regressor like a geomagnetic index, solar wind, or a combination of geomagnetic indices, something that captures the information. You don't even have to know exactly a priori what you're aiming for, because you have methods that are clever enough to pick out the features that are important and recombine them. So you train this neural network, and we used, if you want to know, a slightly deep neural network so that you can get feature abstraction. Bit of a technical term. But if you compare, the bottom three panels there is just Themis data from 3 satellites on a particular day. The black is what you observe. The red is what you teach a neural network to think that your satellite should observe. And lo and behold, they overlap each other almost perfectly. In fact, in our most recent experiments, you get a cross correlation of over 95% between what the model says the satellite should observe to what the satellite actually observes. And this is out of sample data. This is data that's never been seen before by a satellite. Why does that happen? It happens because with a model like a neural network, you're actually able to capture the internal dynamics of the system. It actually does happen. And in fact, if I fast forward here, what you see is a 3-dimensional model of the plasma sphere. It's entirely dynamic. It is entirely data-driven. There's no physics-based model running in the background. It's not assimilative. It's not like here's what a model says and here's what data says, and you sort of fuse them together in an optimal way. This is purely data-driven, and it's not even data-driven by that much data. That's the critical point, is that this is sort of a minimum case scenario. The model on the left is equatorial predominantly. It's driven by only Themis data, A, D, and E, for a couple of years. Model on the right is off-equatorial, so we had to use satellites that measure off-equatorial. So that has IC, CRESS, polar, and image. And of course, on the equator, those images are grouped fairly well. Okay? And so 3-dimensional model of the plasma sphere. Now we're just talking about a single quantity, number density, but you can do it for any quantity. Right? The model doesn't care. Here's an example of whistle mode chorus waves on the left. So now we have a dynamic model. This is again a very early prototype model that I built 2015, 16. My postdoc has now built much more sophisticated models of this. Hiss waves are on the right. Any quantity you can think of that is being measured, you can just simply use the same methodology, right? And the methodology is in its infancy too. This is, again, the minimum case scenario. Okay? So this is the basis of the system. I'm being shepherded off the stage. We can use these sorts of models in science. You can make discoveries directly from your models. You can feed them into other models that are physics-based if you don't have enough data. And so with that, let me leave you with my title, Virtual Space. Imagine just flying through a virtual space environment where every instrument that has ever been flown has been resurrected. And you can kind of see, at least in a statistical or in an average sense, what that instrument should have seen in that space at that time for those conditions. We can do this. The points there are, we could be doing this now. But this is not a grand vision of, invest $100 million. Invest $1 million. Right? We do need some time, we do need some effort that goes into this, but we have all the data right now. The data has been collected, it's been archived, it could be revived and be made extremely usable. We have the computing power and memory, we have the algorithms available, and it's something that I believe points the way to future innovation in at least in space physics, if not more. Thank you.
One question? Can I ask a quick question?
Of course.
I mean, this is an old question, I think, but the neural net knows the answer. To what extent is that knowledge?
Say what?
The neural network knows how to predict the future.
Yes.
To what extent does that constitute knowledge, human knowledge, versus just a machine that does correlation, more or less?
Well, perhaps that's that question is a little unfair. I mean, think about the dial plots that we saw. To what degree do those dial plots predict the future, right? And so, so we have something that grows with increasing data and is able to produce more and more accurate specifications or guesses as to what should be there. It's not going to give you insight. It doesn't. It's a tool, right? And it's a tool that that we use. And I haven't spoken about this much, but with a little toy model that is very lightweight computationally, that you can perform experiments on, you can actually find new things. And we sort of have. And I think it's just the beginning.
There was one more, actually. I didn't want
sorry.
to interrupt. Go ahead.
Yes.
You've got all these wonderful models and all these wonderful graphics and stuff that you're showing. But in order to validate that, you're still going to have to publish it on a piece of paper if you want to be believed. If you want to be believed, in some ways you're back to your diaphragm again. Isn't this publishing on paper part of the problem that we have too? I mean, we've been doing it for how many hundred years now?
Publishing on paper. Well, there was publishing on papyrus before that, and clay tablets. But okay, my ultimate aim is not necessarily publishing it on paper. It's to develop science. So I unfortunately have to communicate it on paper, but that's not the aim. I'm showing you what I've done. The point is to do what I do, not to, communicating is just showing you, pointing you to the good stuff. I hope that makes sense.
Thanks very much, Jacob. All right, final talk of the session. Last but not least, Eric Donovan's, he's going to tell us about the thing we need, which I assume is more than free beer at the poster session. Or?
Well, that's a good start. Thank you, Josh. Thank you to the conveners for giving me a slot to talk. My talk outline is that I'm going to criticize our field, and then I'm going to make a suggestion. That's the outline of my talk, okay? This first slide is a slide I've shown many times before, and it is really sort of a list of solar missions and a list of geospace missions. And one point I'd like to make is that solar physicists, as we saw 2 talks ago, image the sun, and they image the sun very well and very inspirationally and in ways that really inform solar science. In geospace, we have focused the majority of our resources, at least in space, at drilling into the distribution function and plasma waves and so on, and we have, I would say, left ourselves somewhat challenged in terms of the view of geospace at the system level dynamics, and creating that multi-point kind of observation that Allison referred to earlier on. How do I?
I'm going to use this.
I'm going to use this.
Yeah, press one of those buttons.
Okay, so when we talk about our science and we try to, argue our science, we always start from something like societal imperatives, and then we have questions that link societal imperatives to our research goals. We come up with requirements, and then we dream up infrastructure, and sometimes this is a little bit disingenuous because I kind of start from all sky imagers, for instance, go up and find a societal imperative and work down. But this is kind of how this works at really all levels in what we do. I would say that we spend too much time in meetings like this thinking about societal imperatives, that we have a nice set of documents in the form of decadal surveys and so on that outline the societal imperatives that our field are trying to address. These are things like save the world, discover, and inspire. Right, and then you will find things like in the National Academy's decadal survey, things like these 4 science goals for the next decade. We're in this next decade, and what I'm talking about here is really addressing things that would fall under goal 2, which is the dynamics of coupling, of Earth's magnetosphere, ionosphere, and atmosphere, and the response to the solar and terrestrial inputs, and Goal 4, which is to discover and characterize fundamental processes that occur both within the heliosphere and throughout the universe. I'll skip that one. And, you know, the theme of what I talk about actually over and over again, there's not going to be any surprises here, but maybe I can just say it louder and clearer this time, and then you guys will give me my $3 billion that I'm going to ask for at the end. Okay? First of all, what I'm addressing is a gap that I claim we have in our field, and that is that there really is an unexplored range of scales between small kinetic scales and global, and that we lack simultaneous multi-parameter imaging across those scales. Because we don't have that, there are a whole host of fundamental questions that, in spite of many, many missions that have carried out beautiful in situ observations in geospace, we have not been able to answer despite 50 years plus working on these problems. These are highly relevant to space weather because what I'm talking about are the scales and the processes by which the kinetic scale processes spin up to have global scale consequences. And so I think there's no problem making the case for what I'm talking about. Now, as I say, you know, I mean, this is not anywhere near as nice as the movies that we saw 2 talks ago, but solar physicists have given us images of the sun in multiple wavelengths with exquisite detail and spatial and temporal resolution, and they've been doing that really for decades. And you can look at this, you know, you can drill in and you can look at a flare, and you can look at it in multiple wavelengths, and you can look at all the temporal and spatial scales that seem to matter. And on top of that, these movies, they inform the science, but they also inspire. They've created a movie of their system, right, that inspires the public and that is really valuable in terms of making their science go and their science saleable. Now I'm just going to say, you know, we can actually spin a very positive view, and as somebody who likes to go out and get money for things to do in space and on the ground, you know, we have to, you know, I like to say I spend a lot of time in my job telling people how great what we're doing is, and then because I want to do more, I spend a lot of time telling people how inadequate what we're doing is because we want to do more, right? What I'm showing you here is we can look at global auroral images and time sequences of global auroral images. This is from a paper by Mike Henderson back in 2006, and this is just a sequence of images from the image FUV WIC camera. And we can also look at things like, I'll show a movie like this often where I'm showing the ground tracks or the magnetic footprints of SWARM, RBSP, and Themis over the really impressive network of fields of view of cameras in North America, and you know, the AMISR radars and the Millstone Hill radar and so on. And so you can start to see that we have these lots of satellites, we have lots of ground-based observations, and that we're really starting to put all of this together in ways that are fundamentally new. That is very true, right? I'm not saying something that isn't true when I say this. And then sometimes it all comes together in a really nice way, and you know, in this case situation back in 2008 when it was clear across all of North America, all of Canada at least, and you know, there was the very active aurora, and we create these movies of really high time and space resolution auroral movies, you know, on a scale that people have not seen before, meaning spatial extent, combined with that space and time resolution. Now, of course, the reality is also a little bit, maybe when I talk about the challenges that we face, and this is a figure, and I want to be very, very clear that this figure is very dear to my heart. It comes from Larry Lyon's group. It uses data from my group and from Kazuo Shiikawa, and from our optical imagers, and it supports really good science. But if you really look at this and compare this to the picture that you see of the sun in the solar physicist imagers, you can start to see that what we're stitching together here are images from 3 different kinds of cameras. One red line camera calibrated in one way from Japan, one red line camera calibrated in another way from Calgary, and a white light Themis ASI from Berkeley and operated by the University of Calgary group. And that's superposed on that is a convection pattern, but that convection pattern is very small within the field of view of one superdarn radar, and it's line of sight velocities, not vector velocities, okay? And so when you start to look at this, I would say that we've left ourselves somewhat exposed in terms of our ability to really talk about the processes that we're studying. We also have this situation where we have tried to approach our multi-scale dynamics by looking at things we would see from an observatory on the ground, like Sonderstrom or ISCAT or AMISR or Pfizer, for instance, and that we would surround it by instruments and we would drill into the region of space above that one location and get all kinds of information about the small scales, and then we would get the global scales from systems like SuperDarn or SuperMag or Ampere or image FUV, for instance, right? And then what we found, I would say, one of the sort of interesting discoveries of the Themis era, which really came by way of the Themis white light imagers, was this sort of new view into a set of processes that were unfolding in seconds or minutes, but unfolding over areas that were far too large to be seen from one place on the ground, but involved space and time scales that could not even come close to be captured by the systems that we were using for the large-scale pictures before. And so this is this unexplored range of space and time scales that I talk about frequently. We see into it with the white light data now. We're starting to see into it with some other systems, but this is a place where there's some rich physics that we can go after if we could really elucidate things there. Now, if we come back to the image FUV images, you know, if I look at this, you know, these images actually have relatively poor spatial resolution. It's a great instrument, it was a great mission, but we're talking about 200 or 300 kilometer spatial resolution if you really look at the data honestly. On top of that, it's highly compromised. You lose the aurora on the day side with this instrument, and on top of that, you can't really trust that you know where the open-close boundary or the polar cap boundary is in these images because there's a threshold issue, right? And so the kind of information that we would use if you want to just, for instance, have a time series of the open flux, it would be a natural thing to get from a time series of global auroral images. I would say that we as a field have never created a legitimate time series of the open magnetic flux, one of the main things that drives almost all of the physics that we do in our system, right? And so we have not been fair to ourselves as a field in terms of creating the data that we need to look at the system, you know, our system on the system level. And I would not want to restrict, you know, myself just to criticizing my own data or the image FUV data. I would say that if you look at SuperMag and you look at Ampere and you look at SuperDarn, these are fantastic tools, and we've done the best with the resources that we've managed to eke together to create our global multi-scale view, but they actually aren't enough to capture the dynamics in a way that what I would say echo and compete with the way the solar physicists have captured their system level dynamics with what they do, okay? Now that of course is not restricted to the view of the magnetosphere or geospace as projected on the ionosphere. It's also true if you start to go out in the magnetosphere, and one of the things that I'm always fond of saying that, you know, if you look at the situation where we're looking at a substorm expansion phase onset, you know, with 9 spacecraft, including the 8 spacecraft, including the 5 Themis spacecraft. What those 8 spacecraft, you know, really have done is, you know, started to inform us about a lot of what's going on in the substorm expansion phase onset. We've explored a lot of auroral processes and drivers. We've also discovered that the magnetosphere is very big, right? And that's been one of the biggest discoveries, I would say, of this you know, heliophysics system observatory that we're now living with. So I assert that we have this simultaneous multi-parameter view that is really rich science territory for us to go after. I think there is this, you know, unexplored range of space and time scales. We need to do this in multiple parameters. We need to do this in the magnetosphere. And we also need to go after some important key parameters like the time series of the open magnetic flux, as opposed to just proxies that we infer from other things. To address this, I've been, you know, I actually suggest that we need to devote some significant resources to really revamping the way we've been doing ground-based observations. I've suggested this idea of Skynet, you know, which would be just a system deployed across central Canada and down into the United States, where we would not think about, well, I have all sky imagers and so has magnetometers and so on, but rather we would actually construct the list of parameters that we really need to get with things like the electron and proton precipitation, electric field convection, conductance, and so on, and then create the instrument network that would give us this data cube and this time-evolving data cube from the ground on the continent scale. I also believe that at the same time, we have to create that multi-point view of geospace in situ that Allison referred to earlier on, and I mean something like magnetospheric constellation, where you would imagine putting 100 satellites out in the magnetosphere, but closer together than we might normally think of putting such satellites. And at the same time, I also envision Ravens with 2 Molniya orbiting satellites giving us a 24/7 view of the global aurora in multiple wavelengths, you know, on an ongoing basis. And, you know, I've put down $3 billion here. There are obviously lots of stuff that we could do to make that cost a lot less money, but my overall message is that we spend $1 billion fairly routinely on major satellite missions, and that in geospace, we have sold ourselves short in terms of creating the movie of our system. And that's one thing that I think we should give very serious consideration to in the future, because we have to image our system, we have to get that movie, we have to use that to sell us ourselves to the public and also understand the system that we study. Thank you.
Thanks, sir. All right, we got time for a question or two, if there's anything. I certainly have one, sort of a comment. It's in, let's see, within, this type of research is funded under the atmospheric and geospace section at the NSF. So it's really the atmospheric people that you would want to, bring into this. And their physics is fluid all the way down.
Yes.
And as you've indicated, you go down to the kinetic scales and we have a completely different, it's like a phase change. It's a completely different set of physics. And I guess my comment is we know what those scales are too.
Yes.
And so we kind of know exactly what type of distributed network we need. We know the instabilities, we know their dispersion relations and so forth, and this can actually feed back to the information theoretic part of how you design a network.
Yeah, and I think, I think that's absolutely true. And I would also say that, what we really need to do is actually identify the parameters that we know we have to measure and go after them, right? Because we have to know things like the convection electric field at multiple altitudes, right? And I mean, we just basically invoke a whole host of assumptions that we have to, because we've allowed ourselves to live within too small a cost envelope. And I realize that my message is a bit orthogonal when people are talking about a cost-constrained environment, and I'm not good at recognizing a cost-constrained environment, but I think.
when they're needed. Because the kind of approach that I think Jacob talked about is how we're going to be able to test better what the sensitivities are to the various data sets and data resolutions and qualities needed to make the progress we want to make. I think that we need both of them.
Well, I think I would actually build on that, and I would say that so Larry talked about using models with data to actually address what do we need to measure, right? Effectively using what we had. The one pitfall that I would say is that on the one hand, we have very valuable data and great data to address great science with. That's undeniably true. But on the other hand, I think we have not recognized that we haven't done things that planetary scientists have done and solar scientists have done. We have actually short-sold the imaging in the last 30 years in our field. I actually believe that's fundamentally true, and that we have, that needs to be addressed to sell our field in the future. Let's carry this on into the break. I think we've gone far enough. I would like to thank all the speakers for a great set of talks. And we have a follow-up poster session, so stop by that tomorrow.